Hey everyone, so in this lecture, I'm going to be giving you an overview of probability distributions, at least to the level that we'll need for the purposes of this course. So in this course, a lot of what we've been covering is deterministic models. So models for which, given a set of parameters, we get the same result every time we evaluate them. So for example, I've pictured here a population which is exhibiting density-dependent growth. So that's as the population size increases, the per individual growth rate decreases, so that over time the population reaches a carrying capacity. If I rerun the code I use to simulate this population, I'll get the same curve every time. The real world is complex, and even if we think we found a model which provides a good approximation of how a natural phenomena or a population will behave, random variation in the environment and in demographic processes such as births and deaths can cause natural systems to depart from our expectations. So these departures can matter a lot. Here I'm showing 100 simulations where birth and deaths vary randomly. What we can see is that in some of these populations, the population actually declines to extinction. So here's another problem. Sometimes we don't start with a deterministic model and some parameters. Sometimes we start with data from the real world. In this case, it'd be nice to be able to have a defensible method for finding parameters that provide a good fit between our idealized model and the data without just playing with the model until it looks right. So this former use case is an example of what we'll call stochastic modeling, and the latter is what you're probably familiar with as statistical modeling. So for both these problems, we need probabilistic models, models which are governed by probability distributions, which specify some values as likely and other values as unlikely or impossible, instead of just choosing fixed values. So this means that some part of both stochastic and statistical modeling is going to involve random variables. So a random variable is simply the outcome of a random or a stochastic process. In a statistical model, the random variable is usually the response variable that we're interested in understanding, which could be the number of prey eaten by a predator or the number of fish recruits in a given year. In a stochastic model, we might choose to make the number of births per female deer a random variable, or the distance that juvenile fish drift about in the water column before settling onto a reef. One very simple example is the roll of a die. So in this case, the die itself, which we'll denote with a capital X, is our random variable. The possible outcomes of the roll of a die, which we'll denote with a lowercase x, are 1 through 6. We can also assign probabilities to each of the outcomes of the random variable x. We'll denote this the probability p that our random variable capital X equals a given outcome lowercase x. For a fair die, this is just 1/6 for each outcome 1 through 6. So what we've just defined here is called a probability distribution. Now we break up random variables and their probability distributions in two types. Variables are either discrete, which means that there's a fixed number of possible outcomes, or they're continuous. So let's take our die roll. This is a discrete random variable because we can count the number of possible values it can take on, which is 6. We're going to define two functions for this variable. The first is the probability mass function, which we denote with a lowercase f. If I give my probability mass function a value, lowercase x, 1 through 6, it will tell me the probability that my random variable uppercase x equals that value. So in this case, in a fair die roll, right, if I give this function 1, it will give me back 1/6. Same deal for 2, 3, 4, 5, and 6. In all cases, the probability mass function evaluates to 1/6. So this is a discrete uniform distribution in this case. The other way that we can define our random variable is its cumulative distribution function, which we denote with an uppercase F. If I give the cumulative distribution function a value x, it will give me the probability that my random variable is less than or equal to that value. So for a die roll, the probability that x is less than or equal to 1 is 1/6. The probability that x is less than or equal to 2 is 2/6, and so on. The maximum value that our cumulative distribution can take on, and actually the maximum value that it must take on, is 1. If I roll a die, the probability the outcome is 6 or less is 1. So another way of stating this is that the summed probability of all possible outcomes from a probability mass function must equal 1. Now, conceptually, continuous random variables are a bit harder. They don't have a countable number of outcomes. They have infinitely many possible outcomes. Because there are infinitely many possible outcomes, the probability of any one outcome is 0. So think about it this way. You go outside and you measure the temperature with a thermometer that is accurate to infinitely many decimal places. On average, in your area, it's about 60 degrees Fahrenheit, and it's pretty consistent year-round. So you expect that today it'll also be about 60 degrees. But you measure the temperature and you find it's 60.00001 degrees. You do that every day for your whole life, and even though the temperature is pretty close to 60 degrees most days, it's never exactly 60 degrees. When a variable can take on any possible value, the probability of any specific value is 0. But if you went outside and you recorded the temperature every day, you could tell me that the average was 60 degrees, and if the temperature values were symmetrically dispersed around your average, you could tell me that the probability that I go out and sample a temperature value less than or equal to 60 degrees is about 0.5. You could also probably tell me the probability that the temperature is less than 58 or less than 62. So this is known as the cumulative distribution function. Here it is pictured for a normal distribution with a mean 0 and a standard deviation 1, which is also known as the standard normal distribution. If you look at the value of the cumulative distribution function at the mean of 0, you can see that it's 0.5, which means that there's a 50% probability that a value we draw randomly from a standard normal distribution will be less than or equal to 0. Similarly, there's an almost 0 probability of getting values less than -3, and there's an almost 100% chance that if we draw a value from a standard normal distribution, it will be less than 3. So what you're probably used to seeing is this. This is the probability density function, and it's actually the derivative of the cumulative distribution function. While the probability density is not a probability, we can use it in a similar way when we're doing maximum likelihood estimation. It can also be interpreted in a somewhat similar way. So for example, the probability that we draw a value of exactly 0 from the standard normal distribution is 0. But looking at the density function, we can tell that if we draw a value from a standard normal, it's more likely to be around 0 than it is to be around, say, -2. There's a bunch of different properties of random variables that we can go over, but for today, I'll just mention one, which is the expectation. The expectation in the discrete case is the sum of all possible values of a random variable weighted by their probabilities. In the continuous case, it's the integral of all of the possible values of a random variable multiplied by their probability density. The expectation is a really nice intuitive description, though, which is just the long-term average. So if we took an infinite number of samples from a standard normal distribution, the average would be 0. The expectation is what we expect the average of our random variable to be in large samples. So for the rest of this short lecture, I'm going to focus on random variables and probability distributions as we might use them in the context of a statistical model in ecology. So let's start with a simple example, linear regression. So here's a plot of some x and y values with a regression line drawn through them. We're going to assume that y, the response variable, is a random or a stochastic variable, but x is deterministic. We're going to break this model up into two parts. The first is what we'll call the stochastic part of the model. In the case of linear regression, we'll state that our response variable y is normally distributed around a mean mu with a standard deviation sigma. Then we have a deterministic part of the model. For a linear regression, the deterministic part is a line with an intercept alpha and a slope beta times some x value. So this formulation of regression is equivalent to the one you're probably used to, where y equals alpha plus beta times x plus error, where the error is normally distributed with mean 0. But in this formulation, we've written an expression for one of the parameters in our distribution so that it's a function of our deterministic model, so that mu is a function of alpha plus beta x. For all statistical models we build, we're going to assume that the response variable is a random variable, and we're going to link it to a deterministic component. So let's go through a few distributions that you'll see used frequently in ecology. The first is the Bernoulli distribution. This is essentially the outcome of a weighted coin flip. The Bernoulli distribution has only one parameter, which is p, and only two possible outcomes, which are written here as 0 or 1, but they could be heads or tails, or they could be whether a species is present or absent at a site. If p equals 0.4, for example, The probability that the outcome of our Bernoulli distribution is 1 is 0.4, and the probability that it's 0 is 0.6. So one place that we often use the Bernoulli distribution, as you might have guessed, are species distribution models. So let's say that we sampled a bunch of sites along a coastline and across a gradient of temperature, and we recorded whether we saw any rainbow parrotfish at each site. So we noticed that for the higher temperatures, we almost always observed rainbow parrotfish, but at the lower temperatures, they're almost always absent. We want to model the probability that we observe random parrotfish as a function of temperature. So in this case, whether or not we've observed rainbow parrotfish is a Bernoulli random variable with a probability of occurrence p. Just as in linear regression, p is a function of an intercept, a slope, and our x variable, which in this case is temperature. But there's a slight problem here. Since p has to be between 0 and 1, and if we just fit a line, then there's going to be probabilities that are, possibly negative or greater than 1. So we'll apply something here called the logistic function, which will shrink values outside of 0 and 1 to within those bounds. This is called intuitively a logistic regression, and for linear functions, it produces these really nice curves, like you see here. You might also have seen this model written with the logit function, which is the inverse of a logistic function, which is why this model is also known as a Bernoulli generalized linear model with a logit link. A closely related distribution is the binomial, and it represents the outcome of n independent Bernoulli trials, each with a probability p. So say I asked you to flip a coin 10 times and record the number of heads, and then repeat. The number of heads in each of those 10 coin flips would be a binomial variable. As you can imagine, we can also use the binomial distribution for modeling patterns of species occurrence. So say that at each of our sites, we marked fish as present or absent along 3 different transects. This would be the same logistic model as before, only instead of our observation representing the outcome of a Bernoulli distribution, it would represent the outcome of a binomial distribution with n equals 3. So this equation for p would be the same. And here's another example, which is one we'll work through in more detail next week. So say we want to estimate the functional response, the relationship between prey density and the rate of prey consumption by a predator. For all sorts of multi-species and ecosystem level fisheries models, this is a really important component that describes the interactions between predators and prey. Well, if we stock a bunch of fish tanks with different numbers of prey fish, and we hold the number of predators in each tank constant, then the number of prey eaten over a fixed amount of time is a binomial variable where n is the initial number of prey. We could link p to a functional response, such as the Howling type 2 response, which is a really common model in which the rate of prey consumption reaches an asymptote as the prey density increases. It has 2 parameters, which are the attack rate a and handling time h. So these would be our model parameters instead of the intercept and the slope, like in the last 2 examples. So another distribution you might have run into if you've ever worked with ecological data is the Poisson distribution, which is discrete. The Poisson distribution expresses the number of events that happen in a fixed amount of time if they happen at a fixed mean rate. So for example, if we assume that I'm sitting at my desk beside the window 8 hours a day, and dogs walk by my house, with their humans, obviously, about every 30 minutes, the number of dogs I observe in a given day would be Poisson distributed with a mean of 16, because dogs pass once every half hour for 8 hours. Even when we're not observing something for a fixed amount of time, it turns out the Poisson distribution is often a good choice. So we might use it to model the number of sea stars on a bunch of transects that we've done of fixed length, for example. The Poisson distribution covers only non-negative integer values and has only one parameter, which is lambda. Lambda is both the mean and the variance, which for count data often makes a lot of sense because the mean tends to increase with the variance. So for sites where there aren't that many sea stars, we might observe 1 or 2 on most transects, but for places where the average number of sea stars per transect is like 1,000, we might observe 900 on one transect and 1,100 on the next. Or say, for example, that you've gone out for a couple hours every month of the year and you've counted some migratory bird or another, and you found that the number of birds peaked in the summer. If your data followed something like a Poisson distribution, they might look like this. So there's two things I want to point out here. The first is that the months with higher means also have a lot more spread, as we'd expect from a Poisson distribution, where the variance increases with the mean. And the second is that in the months with fewer birds, the data are more skewed, whereas in months with more birds, the Poisson distribution becomes much less skewed. So that's a pretty typical feature of count data too, and it's intuitive because if we can't have negative counts and the mean of our count data is close to zero, then obviously most of the individual counts also have to be close to zero. That's about all I want to say about the Poisson distribution, but I do want to add that for cases where the mean and the variance of our data don't scale together in a one-to-one fashion, which is what we assume with the Poisson distribution, there's some frequently used alternatives. The first is the negative binomial distribution, which despite its name is essentially a Poisson distribution with an extra parameter to increase or decrease the variance. Then the other is the zero inflated Poisson distribution, which, as its name suggests, can be used when the data have a lot of zeros in excess of what we'd otherwise expect from a Poisson distribution, which is frequently the case for species abundance data. However, I do want to note that it can be difficult to choose between these when you're building a model. So for instance, this data looks zero inflated. A Poisson distribution with counts this high shouldn't also have this many zeros. But actually, all this is a mixture of the February and the May data from the previous slide, and both of those are Poisson distributed. So if we fit a model which correctly divided these data according to the months that they came from, a Poisson distribution would be the correct choice. So choosing between these distributions when you're building a model can often be tricky. So there's a bunch of other distributions we could talk about. The last one, and probably the most important one that I want to mention, is the normal distribution, which you're likely familiar with. The thing about the normal distribution is that it isn't just the default choice for no reason. It's used so often partly because it arises so often in nature, even if the processes that generate it aren't normal in nature. So for example, let's look at the Poisson distribution with lambda equals 5 and the binomial distribution with n equals 10 and p equals 0.6, which are both distributions that you've seen in the last few slides. Even if you've never seen these before, they look pretty familiar, right? Well, here's the standard normal distribution for comparison. It turns out that as n becomes large in the binomial and as lambda becomes large in the Poisson, both of these distributions converge to a normal distribution. And they're not the only distribution that does that. So frequently, the normal distribution is a good choice, even for data that are not normal in origin. And often, when all we have is a model which gives us an equation for our expected mean, and we know that there's some variance around that mean, the normal distribution is the first thing we'll try. The last thing I'll add about the normal distribution is that frequently the data themselves are not normal, but the log of those data are. So this arises whenever errors are multiplicative instead of additive. So for example, good or bad years multiply the survivorship of a cohort of larval fish. So recruitment data are rarely normally distributed, but the log of those data frequently are. In which case we say that our data are log normal, and we can either take the log of our observations and fit them to a normal distribution, or we can use the log normal distribution. In most cases, it's not worth distinguishing between these two approaches. Luckily, R has all of these distributions and more built in. You can type !distributions in the R console if you want to see all the distributions built into base R. We'll also be covering a couple more distributions in the lab. So for each distribution, R usually provides 4 functions. The first has the D prefix. In this case, in the case of the normal distribution, for example, it's D norm. The D functions give the probability mass or density function. The P functions give the cumulative distribution function. The Q or quantile functions take the inverse cumulative distribution function. We'll talk about what this is in a follow-up lecture when we talk about confidence intervals. And then finally, the R functions allow us to generate random variables from that distribution. So if, for example, we want to plot the probability density function of the standard normal, we could do that by specifying a range of x values, specifying our mean, mu, and our standard deviation sigma, which for standard normal are 0 and 1, and then giving the d-norm function of our x values, our mean, and our standard deviation. We can plot this distribution with the basic plot function. So that's all for the first part of this lecture. In the next part, we'll cover the likelihood function and maximum likelihood estimation of our model parameters. And then the third part, we'll go over some methods to characterize uncertainty in parameters.